Welcome, good morning, everybody, or whatever time zone you're in. Thank you very much for inviting me in this workshop, which is clearly a very hot topic at the moment, both in academia and industry. So I'm going to talk about symbolic machine learning, and then in the first part of my talk, and the second part, its role in the neuro-symbolic AI, following what has been said, which is the focus of the workshop on how we can do compositional AI, where we actually use toolkits, different systems put together. Okay, so if we look at the artificial intelligence landscape, this is just not supposed to be comprehensive, but some of the key area we can see that artificial intelligence really divided into big subfield, which one is machine learning, and the other is the symbolic or model-based AI, or the old good-fashioned AI, how people sometimes refer it. And there are different streams of research in these two fields, and in particular, what has been at the very sort of hot of the press is actually the development of deep learning systems, or advanced deep reinforcement learning systems to tackle real-world problems. But from the point of view of the symbolic AI, there's quite a lot of work is done in the context of knowledge representations, answer set programming as one of these paradigm, reasoning, planning, and symbolic learning. So I would like to concentrate in my talk on this part of the intersection, and what I mean particularly for neuro-symbolic learning, which is this is a term which is used in many different type of approaches and meaning slightly different things, is I will in particular concentrate in the second part of my talk on the integration and compositionality of deep learning with symbolic learning and reinforcement learning with symbolic learning, okay? So why this neuro-symbolic learning in this particular focus? As we just heard about it, which is the focus of this workshop, machine learning has got a lot of hype in news and in industry and in academia, and clearly it's because it's shown to have incredible advantages, in particular in learning predictive models from unstructured data, and sometimes performing even better than humans. But if we all know that it is kind of a system, so if some of you attended the joint conference on learning and reasoning last week, and a talk of Gary Marcus was clearly put that these kind of systems are actually subject to very strong limitations and drawback. And just to highlight the key ones, so these are systems which are predominantly data-driven, and they are starting recently to be data knowledge-driven, and they find it hard to generalize from the particular the distributions of the training set on which they are actually trained. So they find difficult to do what is called in the literature extrapolation in terms of form of transfer of the knowledge which is learned. And they are therefore vulnerable to data distribution, to shifts in the data distributions. So one of the limitations is the inability of using, or the difficulty, if you like, because some attempt have been made, and maybe we can hear today in the workshop, ability of using existing knowledge, background knowledge on a particular problem in hand, and most importantly, that the model which are learned are not easily interpretable by humans. So they are called black boxes machines. So they are clearly these are clearly, important drawback when we think that AI is now, and machine learning is ubiquitous and is integrated in all our daily life activities. So if we look at symbolic machine learning on the other end, or people also call it, so one aspect of it is inductive logic programming. So but I would like to keep a more general terminology for that, I'll see in a minute, is that these are approaches which present other advantages, if you like, is the other side of the coin, and they are essentially algorithms and systems that can learn data, learn a predictive model from data and knowledge and the background knowledge. They're able to generalize also from very few examples, and they can also continuously revise the knowledge they have learned. But most importantly, the models which are learned, because they are declaratively represented, they are interpretable to human. Now, of course, nothing comes with a free lunch, And these are systems, so they are perceived in the literature and in industry to have some two major drawbacks, if you like. One is the inability of learning for unstructured data, so they need the data to be formalized in a structural form, in a declarative form, and the inability of scaling up and be robust to noise. Now, if we look at this, the sets of the drawbacks for both of these two angles of machine learning and symbolic machine learning, clearly independent individually, they are not sufficient to be able to tackle real world problem where data can come in different shape and forms, and the task of structural engineer can be a bit harder, right? So what we really would like to is to develop a compositional system, compositional AI approaches that are capable of performing human-like learning. So what do we mean by human-like learning? Is these are just a cognitive activity that look at learning from ability to learn from past experiences, of building models of the environment which can explain observations, make a prediction and reason with the knowledge which has been learned. And as I said, also the advantage of symbolic machine learning, be capable of revising and continuous learning, so updating and evolving the predictive models as new evidence are provided to the systems. But most importantly, we must not forget the interpretability aspect and the ability to communicate the knowledge which has been learned. Right. So what we really need, and this is actually why such workshops is important, is the combinations of different toolkit that can help providing a powerful and faster perceptual classification method through machine learning, deep learning, reinforcement learning. They're capable of doing a very fast pattern recognitions from large quantity of unstructured data or data of different forms, but combining this with also symbolic learning method, which have the advantages of learning more abstract knowledge, which can be generalized and can be explained. So that is really the path, in my view, that AI needs to follow in the years to come. And what I would like to claim in my talk is that symbolic learning is one step closer to perform this human-like learning. And what I'm aiming to show you in this hour or so is advancement that we have made in the area of symbolic machine learning, in particular in terms of increasing the expressivity of the models that these systems can learn. We have made them robust to noise. We have made a little bit more scalable than what the people actually perceive the system to be, and also customizable to domain-specific optimization criteria. Now, because of this advancement, we have been able to apply these systems in a variety of real-world problems. But starting, and you will see during the talk, starting from structured data. So really, more recently, we looked at what about the integration of these systems with other aspects, other tools, other approaches of machine learning that expand the applicability of this compositional AI in domains where data are not necessarily structured. So hopefully I will convince you by the end of the talk that this is a good direction to go forward. So let's, in the first part of the talk, concentrate a little bit about the symbolic machine learning, because I'm not sure how many of you are aware of this recent advancement. And then I'm going to tackle on two applications or two proposed solutions for compositional AI, where we integrate symbolic machine learning with deep learning and symbolic machine learning with reinforcement learning. So if we look at the symbolic machine learning area, so as I said, there are lots of advantages, and the advantages really leverage upon the fact that these algorithms and systems are actually focusing on developing a method for learning the knowledge that is declaratively represented. So the leverage about the big body of work that has been done in knowledge representation, and like the conference that we have at the moment running, and because they have a declaratively represented the knowledge, they can actually be verified. They can actually provide the models or learn models that are underpinned by a rigorous semantics, right? And they can be also interpretable, or you might think a way of automatically translated what has been declaratively learned into some kind of natural language form. And they can support the continuous transfer learning, but they're still a machine learning algorithm. So in a sense, they are systems that learn rather than engineering this this knowledge manually, but this knowledge can be actually learned from existing data, existing evidence, as machine learning other methods do. So just to give an introduction of what is a machine learning problem, what are the components when we actually want to formalize a machine learning task. So these are normally defined as a tuple of a background knowledge. This could well be empty if you want to do just a pure data-driven learning. And a second component is what we call it the hypothesis space, a search space, which is the space of the possible solutions for a given learning task, where our solutions here are sets of possible programs represented in a kind of a declarative language. And of course, this is a supervised machine learning approach, so we need examples, positive examples and negative examples of the knowledge that we wanted to learn, right? But this is the kind of input, if you like, into a learning task. And to define, to control the learning algorithms, so we need a coverage relations definitions. So we needed to be able to say, okay, what is an acceptable solution, acceptable program for our task? This is normally a program within the scope of our search space that we define an input, and that covers all the positive example. It does not cover any of the negative example. This is in the literature referred as completeness and consistency of the program which has been learned. Now, this is a very general way of presenting a learning task. There can be There have been in the literature many different definitions of frameworks, and in particular, different frameworks have been proposed depending upon the representation language which is used to capture the background knowledge and also the knowledge that we want to learn, so the inductive bias that we are using, and depending on the formalization of the examples that we have. This is structure formalization of the examples. But also, most importantly, what defines a different learning task is the notion of coverage. So different notion of coverage have given rise in the literature to different symbolic learning framework. And the example presented here is what we call it a learning from entailment. So where the coverage means that the program that we learn together with the background knowledge has to semantically entail every single example and none of the negative examples, okay? So this is the setting of a symbolic learning task in a very general sense. Just to give a very quick example, one of the typical examples in which these approaches have been used for in the literature, this is about learning regular grammars. And we can think, for instance, wanted to learn grammar of the regular grammar of a language for recognizing sentences, correct sentences in the natural language. So we have, for instance, information and the background knowledge about the data that we have. So suppose our data now are strings, and we can define a search space by defining what kind of concepts of predicate we expect in the head of the rules, what predicate we expect in the body of the rules. Don't worry about it, this plus and minus is irrelevant here. And then also, how do we formalize the examples? So in this context, in learning from entailment, examples are typically facts, individual facts. So a set of positive examples is a set of positive facts, and a set of negative examples is a set of facts, which should not be covered. Sometimes it is also represented the fermentation as failure. And the concept of entailment is just unique over the entire set of examples. But in general, they are divided, right? So given this kind of, in this kind of context, we want to, for instance, to learn the hypothesis space here. The search space tells us we are interested to understand the concept of verb or phrase in terms of concept of verbs and modality in our language. So we want to solve the learning from entailment task, computing some program, some knowledge that together with the background knowledge cover all the positive examples, in this case just one, and none of the negative one. So in this case, this could be an example of a rule definition of a verb or phrase that our program will actually return, our algorithm will actually return. And what you can notice here, that the concept which you learn are the concepts that are directly observed. So this is what's called observation predicate learning. So here in this context, we're doing directly classification, if you like. So we have the example and we want to consider classify these examples, okay? But the power of knowledge representation and reasoning, which is underpinning these algorithms, allow also to do what is called non-observational predicate learning. So we might think to have a problem in which we already have a more complex general knowledge. We already have a definition of what sentences are, what verb phrases are, but this knowledge is incomplete. And we formalize our examples as what is a good sentence versus not a good sentence in our grammar. And in this case, the concept that we learn is about a predicate or a relation that is not directly observed, but is linked to the labels of the data that we have through the background knowledge that we already have. So this is a very powerful approach for doing the knowledge completion in the context of declarative knowledge representation, right? Okay, so if we look at the landscape of symbolic learning systems, and even more recently, there's a meta-goal and meta-interpreted learning approaches. These were very much concentrated on knowledge, on learning programs on knowledge, which is represented within the scope of definite clauses, right? So, so the semantics is monotonic, the algorithms are quite efficient and so forth, but the expressivity of these algorithms is very limited. And these systems are had in order to be able to also integrate with other components in machine learning and AI, they suffered of very key limitations. One is some of the systems were not able to perform a learning of recursive concept. They were not able to support a non-monotonicity in the learning or learning harder constraints, choices and preferences. So in all these kind of construct, which are increasing the specificity of the knowledge that we wanted to learn from the data, are particularly relevant in real world problems, right? And as I said, that there was this kind of perception that these systems at the stage of the literature, state of the art, were actually not very robust to noise in the data and not very much scalable to larger data set of large search spaces. So if we want to go towards this compositionality and leverage the advantages of symbolic learning with also the advantages of machine learning, these are very key major limitations that needs to be overcome, right? And that's where our research has been concentrated. So why do we want to actually perform, why do we bother with increased expressivity? So here I just highlighted some of the key sort of application domain that we actually worked on, where we noticed we needed to have a more expressive program, ability to learn more expressive programs. So in the context of autonomous systems, for instance, the agents do not really have a complete information of the state of the world, so they have to be able to learn about the environment, making the default assumptions. So negation as failure becomes a particular key component in the representation of the knowledge of the models that we are learning. When we want to learn a model to make decisions, and in particular in AI is very important, we want to guarantee safety and correctness of these decisions. So in certain situations, it's actually important to also capture in our learned model constraints about the problem in which this model, the domain in which these models are actually then used. And this is a simple example here, but the problem is much broader. And thirdly, there's another example. So when we do actually AI for the humans in decision making, is actually very important also to do some form of personalization of this decision making. So learning what are the human preferences in order to provide decisions which fit the particular user. Now, this personalization is particularly also important in medical domain. When people talk about the personalized healthcare, and the learning preferences is a particular key problem that we need actually to tackle. So, and this is from a knowledge representation point of view is an example. I'm going to touch on some of this later on. So I'm not, don't worry about the representational language here at the moment. I will pick this up later. So what we have done, we have developed a plethora of systems pushing towards increasing expressivity of the program that we're learning. And we are at the moment, as a state of the art, symbolic so systems that are capable of learning programs expressed in answer set. So taking the advantages of the increased expressivity of answer set programming. And we actually have demonstrated that this kind of approaches, we will call it learning from answer answer set. So LAS framework and ILASP is one of the kind of state-of-the-art in learning answer set programming, are able to basically learn quite complex programs, in particular programs that include choice, constraint, preferences, robust noise, and more recently we also tackle scalability. So we're actually advancing a lot on this and getting these systems ready to be used in this compositionality and the other compositional AI. Okay. So I'm going to briefly tell you some of the characteristics of this state-of-the-art, and then I'll move on with the integration with other machine learning systems. Okay, so how can we learn a more expressive program? So we want a more powerful learning framework here. So not the learning from entailment framework, which I just briefly touched upon before, is not, in the context of monotonic semantics, is not sufficient for us. So what kind of knowledge representation language do we need to use? And how can we define algorithms that can learn knowledge represented in this language? And in order to do this learning, what kind of examples we need? How do we want to structure our data for our algorithms? So in terms of the knowledge representation language, as I said, people are witnessing the power of answer set programming and the advancement done from the point of view of developing efficient solvers for answer set programming. So for those of you who is not necessarily familiar to answer set programming, this is a declarative logic programming paradigm for knowledge representation, where normally people look at a real world problem and they formalize manually. This is the context of engineering this knowledge manually into an answer set program, so that by leveraging a powerful solver that actually can solve such a program, we can compute what they call it answer sets. This answer set includes solutions to the initial real problem. So this is the kind of paradigm of knowledge representation in answer set programming. And for instance, an example, going back to the Sudoku example, I will use this a little bit during my talk. You can think about writing, wanted to create a program that is able to generate all solutions, all solved, if you like, a Sudoku board. So we can think about formalizing, engineering what is the sort of the constraints for being an acceptable, a valid Sudoku board, and then we can then run the solver on this knowledge representation of these constraints, and the solver will generate all the Sudoku board within a given sort of a size of Sudoku board, right? So that's the typical approach of knowledge representation. But we actually want to do learning of this answer set program. So because we want to focus on the symbolic machine learning and not necessarily have the task of continuously manually engineer the knowledge, in particular when systems are embedded, AI systems are embedded in a dynamic environment where this knowledge changes over time. So, and to do the learning as a programming, really we want to approach the problem the other way around of this. So we want to be able to take data which are examples of what could be the answer sets of the program that we wanted to learn, right? And this example might be full answer set or partial answer set, as I see in a minute. And from these examples and some kind of language bias defined the search space, formalize this example into a structured way, which I'm going to tell you how to do that, and then learn some representation knowledge that would accept as models answer sets which cover the example we started from. Okay, so really this is the philosophy of learning answer set programs. And what we need to concentrate is how do we formalize these examples and how do we do this learning? What are the kinds of the state-of-the-art systems for that? So examples in the learning from entailment, examples are really, in the, as I said before, sets of facts. But in our context, the knowledge we want to learn is more expressive. So we expect examples also to be a little bit more expressive, okay? And we capture these examples in what we call it partial interpretations, or you could also think about as partial answer set at the end. That's what it will boils down to be. And a partial interpretation is essentially a set of inclusion facts and exclusion facts. So if we look at our Sudoku examples of a single partial interpretation here, each single data point can be represented as what we think should be true, so the inclusion facts in the answer set of the program that we're learning, and what should be false in that answer set of the program that we're learning. thing. So if we have this particular Sudoku board as a single data point, this would be the structural representation of the example as a partial interpretation. And then, of course, we want to learn programs whose model we said cover, and I haven't given yet the definition of what coverage mean in the context of learning from answer set. And in order to do that, we need actually to understand, once we learn a program and we look at the models of this program, these models have to cover our example. So what does cover mean? The models are answer sets. So therefore, answer set need to extend our partial interpretation, whereby extending we mean that all the things that we expect to be true in our model, in a model, have to be included in this model, and what we expect it to be false should not be included in this model. So once we set this framework, this definition, and this is now an example. For instance, this is a full Sudoku board, and we can, so this is an answer set of a program that we learn about the Sudoku board constraints, and such answer set will clearly extend this particular data point, if you like, okay? So, but what does coverage mean? So to complete the formal definition of a learning from answer set, we need to give this notion of coverage, right? So we know now how to represent examples. We know what we want to learn, which are programs written as a set languages, and what does coverage of our learned program mean? So if you think about now a data set from which to learn this answer set program, these are collections of positive examples, so collection of partial interpretation rather than individual facts, and collections of negative example, so collection negative partial interpretations. And learning an answer set program means learning an ASP program within a given search space that we define in our task, such that, and this is now the crucial point, the advancement that we have made in the learning, symbolic learning, such that for every positive example, we guarantee there must exist an answer set of the program that we learn extended with the background knowledge that will extend the positive example. And for every negative example, there must not be an answer set of our learn program extended with together with the background knowledge that will extend the negative example. Now, why this is important, you might think this is some form of similarity to entailment, but actually it is not at all similar to logic, to learning from entailment, because in this case, we can have a form of brave induction here in terms of coverage of the positive example. So we are not requiring that all positive examples are covered in a particular answer set of our program. So every single example can have at least one answer set that will extend it, and this answer set can be different. So there is a weakening here from the logical learning from entailment in terms of coverage of positive example, which is the brave coverage, brave entailment, similar to brave induction. And in terms of the negative example, we want instead to be much stronger. We wanted to say that no answer set. So here we want to force some form of cautious entailment with respect to the negative example. So this combination of brave induction and cautious induction that has never been proposed is something that we proposed in our, so in my group. So Mark Lowe was my ex-PhD student who actually did this in his PhD. And we actually able to make an incredible advancement in the symbolic learning context, and also from the point of view of compositionality with other machine learning approaches. So that's what essentially the core of learning from answer sets mean. And if we give, for example, to our learner, to our ILAS system, the representation of this positive and negative example in the way I described before, we can actually learn just from very few limited data points, we can actually learn an answer set program now. In this case, this means that every single cell in the Sudoku board will have exactly one value, 1 to 4, because this is a 4x4 board. And the cell, notional cell, is given in the background knowledge of the symbolic learner, all right? So we can talk about what a cell is, we can talk about cell being the same row, same column, same block, which are well-known concepts about the problem domain, and we want to, and we can learn the general integrity constraints that together then with this background knowledge will generate all the answer sets that we know will satisfy these notions of brave coverage with respect to the positive, and none of these answer sets will cover any of the negative example. Okay. So we then, just to give another interesting sort of example of application of symbolic learning, if you look here, we are learning now choice rules, right? We are learning hard constraints. And what about recursion? I was talking about a recursive program before. And so we looked at then the Hamiltonian graph examples because it's a graph typically uses the concept of recursion. And this is a problem that recognizes whether a graph is actually Hamiltonian or not. So in this context, we can take examples which are individual Hamiltonian graphs. So they don't need to be large graphs, so they can be small size graph, if you like. And we have as negative examples of graphs that are not Hamiltonian. And then we can put in the background knowledge some very basic information. So for instance, we want to consider all graphs up to 4 nodes, let's say, as a bounding limited size. And the graph is generated by defining edges and choosing whether there's an edge or not in between these nodes. So if I pick up this background knowledge here and I construct all the answer sites, I will have all graphs, not necessarily Hamiltonian, but all graphs up to size 4, all right, of vertices. Now, what we want to do is classifying which of those graphs are Hamiltonian and which are not Hamiltonian. So now looking at how we formalize this in knowledge representation sense, these examples, using this notion of partial interpretation I was just talking before, we were given a particular Hamiltonian graph, we just say, okay, the characteristics about this data point, which we have 4 nodes, where the edges are, so we define the particular graph, and where the edges are not, right? So basically, what this is fully defined a little bit, if you like, the graph itself, but doesn't need to be a full interpretations on that, right? And so we formalize this negative example, and we can actually learn very limited number of these positive and negative example, quite a complex answer set program now, which has got a choice, has got a recursive rules, and has got a hard constraints, right? So we're combining all of that together. So if you can imagine how large the hypothesis space is, or the search space is in this kind of problem, and going back to the interpretability and the explainability I was talking before, you could think about sort of like translating all of this in the English definition of what actually defines an Hamiltonian graph. That is an Hamiltonian cycle, which is a subset of all the edges of the graph, that every node in the Hamiltonian cycle must be reachable. And so there is a path that goes continuously from the first node. This is Hamiltonian started from node 1 in this case, from the first node to the end, so all the nodes attached, and there is this hard constraints that capture the fact that we pass through the node exactly once, so there are no 2 outgoing edges from any node in the Hamiltonian graph. So this is I wanted to put an example because I want to show the expressivity of the programs that this algorithm can actually learn. All right, and can be now, we can learn this algorithm from small graphs, and because we are at first order level, this is a generalization from the graph that we actually use in our data set. Such knowledge can be used at inference time to classify any graph, if you like, right, on much bigger sizes. So transferability here comes for free. All right, then what instead the machine learning will need to do, right, we'll find that it's very hard. So, okay, but then how can we make this more scalable? So looking at scalability. So examples in this context here that I had before, let me just continue, go 1 second here. So we put it at the background knowledge, which are all graphs of size 4. So you can imagine there are multiple answer sets here, right? So the size of the possible answer sets, the grounding is bigger. So when we do real world problem, we want not to get into the bottleneck of having a large grounding of our program. So how can we improve the scalability of these algorithms? One way that we've done this is by using this concept of context-dependent example. So there is some background knowledge which is only relevant to the particular example, not necessarily to all the examples. So why to put everything into a prior background knowledge? We can actually split the parts of the background knowledge that are relevant for the particular example and combine it with the example itself. So in this case, our examples can be not just a partial interpretation, but just a partial interpretation accompanied with a contextual information, where this context can be any answer set program. Okay, so this is quite a powerful way of representing data point, data information. Okay, and if we have now this more expressive example, we also introduce notions of what does it mean for an answer set to cover. So, and in order to define this coverage with respect to this more expressive example, we need to talk about, so this is a definition of an answer set accepting this example with respect to a given program. So this is the context here. And basically the definition says that an answer set will accepting an example if it's the answer set of this program union the context, so taking into account the contextual information, we can extend the partial interpretation. Now, this is yet another extension done in the framework, in the learning framework for answer sets. So going back to our Hamiltonian graph, in this situation, for instance, we don't need really to represent the background knowledge of all possible graph up to size 4, which will give a lot of, so multiple sort of answer sets that sometimes created a bottleneck of the grounding, but we can actually have an empty background knowledge and just push information about relevant to the each data point into the contextual part, right? So we can actually represent each graph as a contextual information, okay? And we can learn exactly the same thing, exactly the same program. So now the general learning from answer set in the context of context-dependent examples is a bit more complex in its own definition. And we still have the typical tuple of a background knowledge with positive example, negative example, and a search space, which is all possible answer sets, including normal rules, choice rules, constraints. And we really have algorithms now that can compute answer set programs within this search space. They are solutions of a given context-dependent learning task. And the solution would mean there exists at least one answer set for each individual example that accept the example with respect to the background knowledge and the hypothesis. This is the program I was referring before. And there is no accepting answer set of any single negative example, right, with respect to the program that we actually have learned. Now, what's the advantage of that? That when we did actually the application of the evaluation of this new algorithms with respect to this new definition of a learning framework, and we developed something called ILASP iterative algorithm called ILASP2I. If we compare now in terms of increased size of our graphs, if we compare with representation, so Hamiltonian A is a data set where we use the background knowledge and the single partial interpretation, and Hamiltonian B is a representation of the problem, the learning problem, where we use no background knowledge but context-dependent example. So making the background knowledge relevant to the example, linked with the example itself, and using this more advanced learning framework, we are able, in terms of memory and also time, to control some of the exponential growth when the data size becomes bigger. Okay, so there's a clear advantage on this novel sort of algorithms. So the last part of knowledge learning that I haven't touched upon is learning preferences, okay? And this is quite important, as I said before, and actually answer set programming is ideal for that because it can combine reasoning with optimizations and it gives a way of not only computing answer set, but also be able to define what are the most preferred answer sets. So, and this is done in answer set programming with the concept of weak constraints. So, for instance, imagine we are in a domain of suggesting humans a better, a journey from from a point A to a point B, and we have human preferences of what would be the preferred personal way of choosing a journey. So they can be avoiding walking through area with high crime, minimize the number of buses, minimize the distance walk. There can be many different preferences. Each human has got their own independent preferences, right? So, and these concept of preferences can be formalized in answer set programming with weak constraints. So from an answer set programming point of view, we could write this kind of preference models, and the answer sets that are then computed in a particular context, in a particular situation, will give the preferred journey to a particular human that, if you like, minimize violations, if you like, of these weak constraints, okay? So if we give such a weak constraint, so in this case, for instance, this number here is the order of priority. So this is a constraint that need to be first tried to be satisfied, and the answer set programming will compute the answer set that minimize the violations of these constraints. And if there are multiple journeys that satisfy the, with equal, if you like, a penalty, then there will be a second layer of preferences, and then a third layer of preferences, and so forth. So given this kind of a weaker constraints, if we have, for instance, a forward journey, the answer set program will then generate an order over the possible journey and then return to the human the most preferred journey. But of course, this is good if we can engineer, right, this kind of weak constraints. But what we actually do in symbolic machine learning is learning these weak constraints. So how can we do that? The very intuition here at the core of it is that the weak constraints don't change the number of answer sets of a given background knowledge, but rather order these answer sets. So there's no point of adding more examples, more positive or more negative, because we want the same answer sets of our background knowledge, but we want actually to order them. So really examples now are not just sets, but they are ordered pairs of possible journey or partial description of possible journeys, right? And we can give this order pair, and from this ordered, learn the weak constraints that would then, together with the background knowledge, create an ordering of the answer set that accepts the ordered examples given in the data. Okay, so we have applied this in this our journey planning sort of decision support, if you like, a system or app. This was a European project, and you can think about here also a human in the loop type of approach, because the knowledge that is learned is actually explainable, interpretable by human, and we can take the weak constraint and translate them in English. So, and the system can provide some suggestion based on what it thinks the preference of the humans are, and but the human can make choices about the alternative suggestion. Maybe it might refuse what the system is suggesting, because maybe the preference model the system's learning is not really the right one, or because humans change their mind all the time. And in that case, the choice of the human can become now a feedback to the system. So we can automatically generate a counter example to our learned preference model and update our preference model. So this is what I was talking before in terms of continuous learning, revising and updating the knowledge that the system is actually learning. And what we actually demonstrated with the various development of the learning system that we have is that we can actually learn some targeted preference model, if you like. This was a synthetic data generation where just reaching 80% with just 8 counter examples, so 8 times going through this loop, which is quite an interesting, a powerful result. So the human might change their mind, and if we have some target the preference model, we can get to that with a very few data points. So we wanted then to scale it to a large number of examples. So we evaluate our context-dependent approach, as we just said. So preferences can be contextualized. So they are not absolute preferences of the human. So, and this context information can come from sensors, if you like, right? They don't necessarily have to be given manually, right? So there can be a way of combining here machine learning to do that. And if we do that, we actually demonstrated our current system by using context-dependent example is much more efficient in execution time than if we don't use context-dependent examples, right? So I can learn from a reasonably larger number of examples here. Now, what about noise? So now we're at the point where we can cover quite a range of knowledge representation and learning this knowledge representation automatically. But what about when the data that we have actually wrong labels, let's say, so they are noisy per se. So in this case, typically logic-based learning or symbolic machine learning uses the concept of an Occam razor principle, which is like looking for the most compressed programs. And what we do in our systems, in our approach, is actually defining a notion of penalty over the examples, where the penalty identifies the level of certainty of the correctness of that example. So higher penalty means that if that example is not covered, so the hypothesis that will not cover that will be penalized most. So if the penalty value is higher, it means we are more certain. If the penalty value of the example is lower, it means we are less certain, so it's a more noisy example, okay? And then we can define a scoring function upon the possible programs in the hypothesis space as just the compactness of the program plus the sum of the penalties of all the examples that this program does not cover. So if we go back to our journal examples, using wrong label, because a human might thought there was something a preferred journey but was not, we can actually evaluate the effectiveness of this, now it's called ILASP3, but this ILASP system is actually continuously evolving, the effectiveness of our learning algorithm in the presence of how much noisy data we have in our data sets, right? Of course, more noise we have, more data we need to reach a higher level of accuracy, right? Before we had 80%, we have very few examples, but the data were correct, were not noisy, okay? So that is where we are in the symbolic machine learning domain. And we can actually, we demonstrate and compare with any other systems that we overcome two of the very big limitations that I described at the beginning. And this has allowed a plethora of applications that we have done in our in my research group. And I don't have time, unfortunately, to go through all of this, but I want to concentrate now on the compositionality with other machine learning, right? So what about scalability with respect to the search space? And when actually what we wanted to learn is the possible programs are very large. And in order to help more compositionality with machine learning, we actually needed to advance the scalability, not just in terms of example, with the context-dependent example I was just talking before, but advance the scalability with respect to the search space. So when we have large possible programs that we actually want to learn from. So, and in AAAI last year, we published a new system called FastLAS that is actually much more scalable from the point of view of the search space, so the possible program to search. And the principle underneath it is that rather than considering all the possible programs, so they're writing the search space fully, we have a way for computing identifying the sufficient part of the search space, which is a subset, and normally this is much, much smaller than the search space given in input as language bias. And this sufficient subset is guaranteed to contain an optimal solution. So we are not losing the optimality property of our algorithms, but because we are working on a much smaller search space, we are able to be more scalable, right? So we applied to data sets such as the KRHCAI data set, which is about recognizing activities of people meeting in a working environment. And we actually realized that our search space can increase much more with this new system with respect to the ILAP system, where we actually cherry pick a particular language bias to make it scalable. And by searching a bigger space, we also increase the accuracy of the program that we actually learn, okay? So we are also advancing from that point of view. But now we are in the compositionality aspect. What about if this data is actually non-structured? What about in the way that we applied here? This was a good data set because the video came with a manually annotated symbolic representation. But what about if I don't have that, all right? So the next step is, okay, FastLAS is very good, it's scalable, but requires structured data. So we need really machine learning method to be able to do this fast feature extraction of some unstructured data in the real world, and symbolic learning that helps then to generalize and to learn the knowledge that can be transferred from a domain to another domain. So we want to go back to this human-like learning context where actually we want to compose different approaches of machine learning. So I'm going to tackle on two recent work that we have done on that. We are continuing work on that. So this is a space to watch. One aspect, one approach is a hybrid way of integrating deep learning with symbolic learning. And what we wanted to do here in this integration is understanding how robust a symbolic machine learning is in the context where the, if you like, the features of the contextual information of our example is produced by a machine learner, right? That we know machine learning algorithm, deep learning can have noise in the prediction. Sometimes they can predict wrong things even with a very high accuracy. And we also know that these machine learning algorithms are not robust to distributional shift. So in the moment that we take a trained algorithm, a trained deep learning algorithm, if you like, for doing classification of feature structure from images, if we want to apply this now to a slightly different data set, which is outside from the distribution of which the algorithm has been trained upon, would the symbolic learner be able to still learn a robust knowledge? So this is the kind of question we started to explore in the compositionality part of AI work that we're doing. So what we actually looked at, first of all, to start from a feed-forward pipeline architecture, where the feature extractions from the images comes from a deep learning, a neural network, if you like, and the symbolic learner, the abstract knowledge learning, is supported by our FastLAS system, right? So this is again the example of the Subgoal board. So imagine a board is fed into a deep learning architecture as images of digits, in a particular sequence to represent the cells into the Sudoku board. And now the network is pre-trained to recognize digits. So this is what's the MNIST data set that we used here. So we have this prediction of the digits as a contextual information, and we want to learn a classification of what is a valid and what is an invalid Sudoku board, right? So the point is, how do we do this mapping here, all right? So if we were using the old style symbolic machine learning, which is not robust to noise, this would have been harder, right? Because it would be very sensitive to the wrong prediction and will lead to wrong knowledge extractions here, okay? So the technical challenge here is that once we train a neural network on a particular data set and we apply on slightly different data set, the prediction might not be correct. So there is some perturbation in the data and the real data. So the prediction might not be correct. And the data in the real application inference time, it can come from a different distribution than the one used for training. So how can we still learn? Oh, the question is, can we still learn abstract knowledge in the context of this possibly wrong prediction, a longer prediction even with high confidence that comes from a neural network? So we developed a method, a very simple method for automatically generating in this pipeline, in this feed-forward architecture, labeled context-dependent partial interpretation for our symbolic learner. So, and essentially the prediction of the network is on what kind of digits we have in individual cells. So there's a mapping from the classification of the MNIST digit into this symbolic, if you like, latent layer here. And then we actually use the confidence level and an aggregation, a T-norm confidence aggregation function to define the penalty of the particular example. So the example we have now, what is valid and what is invalid, the context of the example is the prediction that the network generates of the digits, and the penalty of the example is an aggregated penalty of the confidence of the digits of the network is making of the digits in the board. All right. So, but this penalty, because in answer set programming numbers have to be integers, this penalty is scaled in a certain way with the flow of multiplication 400 to go back to the integer value. All right. So some results show that if we actually take a pre-trained network and now we perturb the data, so we change the orientation.
Sorry, Ali, you have 3 more minutes, please.
Yeah, okay. So we change the orientation of the data. We can still learn the programs. They are very robust, even up to 80% of data perturbed, if you like, right? So this was quite an interesting result from our point of view. We looked at the interpretability of this program by comparing with baselines, which are pure machine learning. So we use LSTM, we used random forest, another sort of baseline. We use some kind of mechanism for extracting rules from this machine learning architecture, and interpretability is much better in the sense our programs are much more compact. The execution time is a little bit higher than all the others, but we gain in the accuracy, right? So I have a lot of other graphs here just to show that this is actually maintaining still high level accuracy even with a larger board, so we can scale it to a full Sudoku board here. And so there's a paper here available in archive for you to look at all the actually analysis that we did. So now in my last 2 minutes, I would like to just to touch upon very briefly on the integration of symbolic machine learning with reinforcement learning. Now, in this context, we all know that reinforcement learning, you know, it doesn't find it easy to transfer to different domain. Hierarchical reinforcement learning is a promising approach for performing reinforcement learning tasks in terms of decomposition of tasks and subtasks. And one way of doing this decomposition of tasks and subtasks is by representing this decomposition declaratively as automata. And existing a very recent work by Sheila McClare in ICML conference in 2018 showed that if we engineer this automata, which she called the word machine, we are able to get a better sort of reinforcement learning performance. And the type of work that we've done here, how can we learn this automata? How we can interleave a reinforcement learning agent with a symbolic learning of this automata that capture the task decomposition, right? The goal decomposition of the reinforcement learning agent. So there's quite a lot of detail here, but just to give a very brief overview. So this is an example of a grid. So this is from an reinforcement learning point of view, is a partial observable MDP model. And from the decomposition of the task, so the higher level knowledge representation, we talk about automata, which actually look at how we can get to accepting state through decomposing the entire task into sequences of subgoals, so the entire goal into sequences of subgoals. And we develop a mechanism for mapping execution traces of agents in the real environment into symbolic observation traces, right? So there is a massive abstraction here about the real state information into what are just key observable for the particular task. And we're able to learn these automata by feeding to the symbolic learner these traces of observation traces, which can be positive if the agents end up in an accepting state, and negative end up in a dead state, and incomplete if the number of episode steps terminates without getting to the goal, right? Okay, so just very briefly,
seconds, please.
Yes, very briefly, this is how we actually combined there is a lot of detail in the paper, how we do this mapping. This is all automatically done. So we feed the particular environment, we have this language observation, and we generate the automata. And what you can see is that actually the performance compared to the engineered automata, so we compare our system with the engineered one, the performance is actually comparable, but we don't need to engineer all of that. Right, so we applied in 2 different domains, and this is actually, you can go in this our recent JARS paper this year, which has got exhaustive information about how this framework is done, and the technology, the technical challenges we have to overcome, as well as the evaluations results. So in summary, symbolic machine learning, the message I want to give it, has made a giant step forward in the recent state of the art. That we have made this a giant step forward. We can learn a complex knowledge by being more robust to noise. And this is essential for combining with other machine learning approaches, as we have seen in our recent application. And we are not losing the interpretability of the knowledge that we actually learn. So neuro-symbolic learning that does this compositionality is actually a way forward in order to combine the leverages on the features on these great advantages of symbolic machine learning, and also the advantages on deep learning. But in my view, more still needs to be done, and we are currently working on more sort of integrated end-to-end solutions for combining these 2 different approaches. And I would like to thank many collaborators, but in particular the ex-PhD students, PhD students and colleagues that are working on this type of application I described today. So I'm open to questions. Thank you.